Alright everyone, in this video I'm going to show you how to use data science to predict whether a mammogram mass is benign or malignant. Now, why would we want to do this? Well, a lot of unnecessary pain and surgery comes from false positives on mammogram results. If we could develop a more accurate interpretation of these results with data science and machine learning, we can avoid false positives and help a lot of people. So let's, without further ado, dig into some Python code and see how we can actually do this from start to finish, okay? So let's run data science on the public mammogram masses data set from the UC Irvine repo. We have 961 records to work with in this data set, which contain these 6 attributes. So we have what's called a BI-RADS assessment, which has a value of 1 to 5. We have the patient's age in years, which is an integer value. The mass shape, which can be round, oval, lobular, or irregular, with values of 1 through 4 respectively assigned to those. Mass margin of circumscribed, microlobulated, obscured, ill-defined, or spiculated. Again, we have a numerical value for each of those, 1 through 5. Mass density can be high, iso, low, or fat-containing, values 1 through 4 representing those. And a severity value of 0, which is benign, or 1, which indicates malignant. Now, because BI-RADS is an assessment of confidence in the severity classification, we can just go ahead and discard that from our feature set, which leaves us with the remaining features of age, shape, margin, and density. So these are going to be used in our models designed to predict our binomial target variable of severity. Now note, although shape and margin are actually nominal data types, their numerical values do turn out to be functionally ordinal and thus can be used effectively with sklearn. So let's go ahead and get started with data preparation. So we're going to start by loading our data into a pandas data frame and then converting any missing data, which would be indicated by a question mark, into not a number and adding column names as we go. That is what this code is going to do for us here. We run that and look at the head value, and that shows us our data here. Next, we're going to inspect how clean our data is with the pandas describe function. So if we look at the count row up top here, see, this is showing quite a few missing values in our features and targets. So before we go and eliminate all rows with missing data, we want to just observe we'll want to observe all rows with missing data and make sure that there isn't some obvious correlation to the data missing fields. If there is, we want to go back and try and fill in that missing data. So we run this code here to summarize only, or to show only the records that have missing values. And if we just kind of scan through here, there doesn't seem to be a whole lot of correlation. In other words, the missing data just seems to be randomly distributed. So we basically have the green light to use pandas drop NA function to drop rows with missing data. And that's what we're doing here in this code. Okay. And now if we look at the counts, we are left with 830 values for each of these columns, so no more missing data. Good, so that's done. Now, next we're going to convert the pandas data frame feature and target columns into NumPy arrays so that they can be used with sklearn. All right, so we have all classes and all features here. And to further prepare our feature data for use with our models, let's just go ahead and normalize it with sklearn's pre-processing standard scalar function. That's what we're doing here. Okay, now that we have normalized data, as you can see here, let's run it through several models to see which one comes out on top in terms of its accuracy. Starting with decision trees. So we're going to start out by train test splitting our data and fitting a decision tree classifier to the training data. All right, so that's what we're doing here with the train test split. and we import the decision tree classifier from sklearn. Here we're assigning it to the CLF variable, and here we are fitting the decision tree classifier to our training inputs and targets or classes, right? And what we're left with is this here, and we can now evaluate our decision tree classifier's accuracy against our test data. Okay, so we have testing inputs and testing classes. What's the score on that? 73. Okay, not awesome, but now let's see what would happen if, rather than just having a single set of trained test data, we were to use k-fold cross-validation to get a better measure of our model's accuracy. And we do that by importing cross-val score here, running this line of code here. We're going to use a value of 10 for k, and look at the mean on that. So again, we have an accuracy of 73%. So now let's try several other models and see how they do, starting with random forest. Okay, so random forest gives us a mean of k-fold cross-validation scores of 75. Now let's run a support vector machine on it, and we get 79. And that's with a support vector machine kernel of linear, but what would happen if we used some of these other kernels? So if we use RBF, we go up to 80, sigmoid's only 73, and poly is 79. So it looks like the RBF kernel actually is the most accurate with 80.1% accuracy. We can run k-nearest neighbors on this, and it's 78.5% accurate. But before we move on to other models, let's try other k values to see how they perform using k-nearest neighbors. So far, our benchmark with a value of 10 is 78, but can we do better? Well, looks like a value of 7 is giving us 79.4, right? And as we approach 50, doesn't seem like we can really even improve much on that. So if we were to use k-nearest neighbors, we could use a value of 7 for k and do just fine with that. And we'd have 79.4% accuracy. Let's move on to naive Bayes and see how it does using the multinomial naive Bayes method. However, because this requires non-negative values, we're going to have to use min-max scaling on our feature set before running it through our classifier. And we do that here. And once that's done, we can pass it through our classifier using k-fold cross-validation, and we get a mean value of 78%. And finally, if you think about it, we basically just have a two-valued target situation here, which we can run logistic regression on, right? And at the end of the day, look at that, 80.7. So our verdict is the winner for the most accurate model is logistic regression with an accuracy of 80.7%, and with our loser being just a plain vanilla decision tree with an accuracy of 73.6%. So I hope this video helped you to see how we can basically run a data science problem in the healthcare industry from start to finish, use some machine learning models to predict whether a mammogram mass is benign or malignant. Thank you for watching this video. Appreciate it, and have a great rest of your day.